In this chapter, we'll learn how to estimate the interval estimation of population mean, and also we will learn how to determine the sample size. Let's recall from the example 2 of chapter 6, session 2. Now, the highlighted size, the physical size of this area here is the probability of z smaller than 2. And of course, when we talk about z, it is a standardized normal distribution. So if we look it up in the standard normal distribution table, we know that the value of this probability z smaller than 2 equals to 0.9772. Now, if we know the size, the physical size of the area highlighted here equals to 0.9772, then we know that we can find that the size of the area goes beyond the 2 to the right hand of it, this tail here. Okay, this tail, the size of this tail equals to 1 minus 0.9772. Basically, it's 1 minus the highlighted area. 1 minus 0.9772 equals to 0.0228. That is the probability of z bigger than 2. Now let's introduce a new notation. So the 2 here, the number 2 here, is a point on the z-axis. This is a point here, okay? And we know that the probability of z bigger than 2 equals to 0.0228. We're gonna use a notation as following. Z footnote 0.0228 equals to 2. And the footnote comes from here. It's the probability. Okay, the footnote is gonna be the probability. The value of this z 0.0228 equals to 2, and that is the point. So basically, these two connect. Probability of z bigger than 2 equals to 0.0228. Another way to write it is z footnote 0.0228 equals to 2. Now let's do an in-class exercise. We want to find out probability of z bigger than what value equals to 0.05. And that value, actually, we will write it as z 0.05. So please stop this session and take as much time as you need and solve this in-class exercise. Here's how we solve that. Now, if we know probability z bigger than certain value equals to 0.05, then we know the probability of z smaller than this value will equal to 0.95. Okay. Then next we find 0.95 in the body of the standard normal distribution table. So body of the table. So 0.95 is somewhere here. The value of the z value is 1.645. So we know that what we're looking for, the value we're looking for is 1.645, and this point on this z-axis is 1.645. We can write it as z footnote 0.05, 0.5 comes from here, equals to 1.645. Now let's look at another example. Now suppose we're gonna arrange it this way in a normal distribution. We'll have 90% in the middle, and we will have two tails. These two tails are of same size. So the probability, the size of this highlighted tail is 0.05, and this tail is 0.05 as well. So we know that in the middle it will be 0.9, because 0.05 plus 0.9 plus 0.05 equals to 1. Now if the middle part is 1 minus alpha equals to 0.9, and we have two equal sized tails, the left hand is alpha over 2 equals to 0.05, right hand alpha over 2 equals to 0.05. Then we know that alpha over 2 plus 1 minus alpha plus alpha over 2 equals to 0.05 plus 0.9 plus 0.05 equals to 1. Another way to look at this is we specify 1 minus alpha equals to 0.9. Then we calculate alpha equals to 0.1. And then alpha over 2, of course, equals to 0.05. So in this way, if we know the middle, then we know the size of the two tails. So here, alpha over 2 equals to 0.05. So z alpha over 2 equals to z 0.05. From our previous in-class exercise, we know z 0.05 equals to 1.645. So this z value is the point on the z-axis here. Next, if we look up on the normal distribution table, we will find that probability of z smaller than negative 1.645 equals to 0.05. If we know the probability of z smaller than negative 1.645 equals to 0.05, then we will call this point, this is just a notation, negative z 0.05 equals to 1.645. So there's nothing special about it. We just try to keep it consistent, keep the notations consistent. So this point, we're going to call it negative z 0.05. So how do we understand this? Now, if it is left tail, then we're going to write it as negative z, and the footnote comes from here, 0.05. So again, if we look at the complete picture, we'll have 1 minus alpha in the middle equals to 0.9, and alpha over 2 here on the right hand equals to 0.05, another alpha over 2 equals to 0.05. And that's the probabilities. The point on the axis, z-axis, is this point is positive z 0.05 equals to 1.645. And this one, this point, is negative z 0.05 equals to negative 1.645. In general, we're going to write it this way. The middle part is 1 minus alpha. The left hand, alpha over 2. Right hand, alpha over 2. And the point here is positive z alpha over 2. And the negative, point here on the left hand is negative z alpha over 2. And these two are the notations. Now here is another in-class exercise. If we know alpha equals to 0.05, please find the value of 1 minus alpha, alpha over 2, and value of z alpha over 2, as well as the value of negative z alpha over 2. So please use our previous example as your guide to solve this in-class exercise, and take as much as time as you need to finish this. If we have not done that yet, please stop this session for a moment. Now here comes the answer for it. If alpha equals to 0.05, then the middle part equals to 0.95. Alpha over 2 equals to 0.025. And here's 0.025 as well. So the value for this point equals to z 0.05 equals to 1.96. We find this from the standard normal distribution table. And the left hand, negative z alpha over 2 equals to negative z 0.025 equals to negative 1.96. Now we're ready to do the point estimate. Remember that we try to estimate the population parameter mean mu, which we do not know. So we use a sample mean x bar to estimate mu. Since a sample is only a portion of the population, it will not give us the complete information of the population. Hence, the sample mean will not be exactly same as population mean. So we're going to do interval estimate of a population mean. There's two different scenarios. We're going to introduce one by one. One scenario is we know the population sigma and the sample size is bigger than 30. The other scenario is we do not know the population standard deviation. First is the scenario where we know the population standard deviation and the sample size n is bigger than 30. We're going to use this formula. The interval estimate of the population mean mu equals to x bar plus minus z footnote alpha over 2 times the sigma, which is population standard deviation, divided by square root of n, the sample size. So in the notation, we know n is the sample size, sigma is population standard deviation, alpha, 1 minus alpha here is the confidence level. We're going to use an example to illustrate this formula. Here's the example. Discount Sons has 260 retail outlets throughout the state. The firm is evaluating a potential location for a new outlet based in part on the mean annual income of the individuals in the marketing area of the new location. A sample size of n equals to 36 was taken. The sample mean income is $31,100. The population standard deviation is estimated to be $4,500, and the confidence level to be used in this interval estimate is 0.95. So first of all, the confidence level is given as 0.95, so we know 1 minus alpha equals to 0.95. And then we can calculate alpha. Alpha equals to 0.05. Alpha over 2, then we know it equals to 0.025. Z alpha over 2 is the value we need to calculate. So Z alpha over 2 will equal to Z 0.025. It comes from here. equals to 1.96 as we solved in the previous examples and in class exercise. And sigma is the population standard deviation. It is given here as 4,500. N is the sample size, which is given as 36. So now, with this, we're ready to calculate the confidence interval. By the way, when you solve any confidence interval problem, please follow the steps here to lay out all this information in front of you before you use the formula. Now we're ready. Basically, we calculate x bar plus z alpha over 2 times sigma over square root of n. Plug in all the numbers we calculated from the previous slide. X bar equals to 31,100. Z alpha over 2 equals to 1.96. Sigma equals to 4,500. N equals to 36. So it comes to 32,570. And then the next one is x bar minus z alpha over 2 times sigma divided by square root over n. So we plug in all the numbers. We get a 29,630. So we are 95% confident, and that's how we interpret that the interval here contains the population mean. This 95% comes from the problem description, where the confidence level is 95%. So it is between these two numbers, as we just calculated. Or we can write a different way. The 31,100 plus minus 1,470